Welcome to this explainer. Today, we're going to crack the code on literally one of the most misunderstood concepts in all of data. If you've ever seen some wild science headline and thought, wait, how do they actually prove that? Well, you're in exactly the right place. We're going to make this whole thing incredibly simple.
Okay, so let's just dive right in. I want you to picture a super straightforward scenario. Imagine you're sitting at a table and you flip a coin 100 times. Naturally, you're expecting a perfectly fair split, right? 50 heads, 50 tails. But instead, as you tally it all up, something kind of suspicious happens.
You get 60 heads out of those 100 flips. Now, immediately, you've got a mystery on your hands. Is this just pure dumb luck? Or is that coin heavily weighted? Like, are you being cheated here? The real question is, how can we mathematically measure that suspicion?
Well, this perfectly illustrates our mystery. If the coin were completely fair, the math tells us there's only a tiny 3% chance you'd see 60 or more heads just by random luck. The vast majority of the time, you'd get an outcome way closer to that normal 50-50 split. It's that tiny 3% anomaly that really catches our attention.
Section 1. Enter the null hypothesis, the assumption of no effect.
Before we can officially give a name to that 3% chance we just found, we really need to establish a baseline. Statisticians call this the null hypothesis, often written as H0. It's basically the assumption that there's no true effect, no real difference, or that your outcome is literally just pure chance. In plain English, we're just assuming nothing special is happening. So, in our detective story, we assume the coin is completely fair until the data absolutely proves otherwise.
Section 2. Enter the p-value, measuring the unusual. All right, now that we have our baseline locked in, we can finally give a proper name to that tiny 3% probability. Meet the p-value. It is the probability of observing results at least as extreme as yours, assuming the null hypothesis is completely true. Listen, if you only remember one thing from this explainer, make it this. A low p-value just means your results would be highly unlikely if they were solely due to random chance. So in our coin example, that 3% chance, that is our p-value.
Section 3. Passing the threshold, making the call.
So where exactly do we draw the line between a random coincidence and a real effect? Well, researchers compare the p-value to a specific threshold, which is known as a significance level, or alpha. If your p-value drops below 0.05, meaning there's less than a 5% chance of seeing this by pure luck, you officially reject the null hypothesis. It's strong evidence. But if it's 0.05 or higher, the evidence is weak. You fail to reject it, and you kind of just have to assume the coin is actually fair.
But, and this is a massive but, the 0.05 cutoff is just a convention. It's not some universal law of nature. This rule definitely isn't written in stone. For instance, fields like medical trials, where literal lives are on the line, they demand a much stricter 0.01 level. Other fields might be a bit more lenient. Ultimately, it's just a human-made threshold that gets chosen before the experiment even begins.
Section 4. What p-values are not. Busting statistical myths.
Okay, before we go any further, we really need to clear up some major confusion, because honestly, people get p-values wrong all the time. A p-value only tells you how compatible your data is with the assumption of pure chance. That's it. It is absolutely not the probability that the null hypothesis is true, it's not the overall chance your results happen by accident, and most importantly, it is definitely not proof of real-world impact. A tiny p-value doesn't mean you discovered something massive or groundbreaking. It just means you found something mathematically unusual.
Section 5. The step-by-step process, how it's calculated.
So how do researchers actually get this magical number in the real world? Well, the journey basically always follows these exact 5 steps. Step 1, you state the null hypothesis. Step 2, go out and collect your real-world data. Step 3, compute a test statistic, like a z-score or a t-score. Step 4 is finding the actual p-value. And finally, step 5, you compare it to your chosen threshold to make your final call. Literally every single time you see a p-value in a paper, someone went through this exact workflow.
Section 6. The statistical red flag, looking closer.
To really wrap your head around this concept for good, I want you to think of the p-value like a red flag. It doesn't tell you the whole story, not even close, but it signals when your data is unusual enough to look closer. A small p-value doesn't definitively prove your new hypothesis is perfectly true or false. Instead, it acts as an alert system. It's basically waving a giant red flag saying, hey, something unusual is happening in this data.
And because the p-value is really just that, a red flag, you always need to combine it with other tools. You need confidence intervals, which show you the actual range of possible true values, and effect sizes, which tell you if the difference is actually big enough to even matter in the real world. Together, these help you make clear, reliable decisions. The p-value just gets your attention. It's these other tools that do the heavy lifting to give you the whole story.
So here's a little challenge for you. Where will you spot your next statistical red flag? The next time you see some incredibly bold claim in the news about a groundbreaking new study, I want you to ask yourself, are they showing you the whole story, or did they just find a tiny red flag and run with it? Keep this concept in your mental toolkit, and you'll be navigating the world of data like an absolute pro. Keep asking those questions and keep looking for those red flags.